I'm doing a sound check.
Sound check. What the heck?
Sounds like sound, dude. That's the sound of sound. What are they?
There's a mystery short.
So we're going to get into our formal presentation for the TV and have Morgan kick off with the demo of the voice machine. And then we're going to go into Microsoft Circle. And then we'll talk a little bit about our channel
or anybody that wants to talk more about what they're doing. So let's mosey on to the electronics bench. Feel free to freshen up your drinks. We do have a choice of sodas and beer and wine, but you need 5 minutes? Okay.
2 minutes.
You have 5 minutes to mosey from here to Nah.
So we can check it out. So we can switch just like this.
Ready for my close-up.
There you go. That's that, dude.
Twofer.
You're all good, dude.
And
Bo, could you check your control over that camera?
Yes.
Yeah.
So that's your like demo cam.
Yeah.
So
So you'll
you'll
flip it
flip it
around.
around.
Oh,
I'm
yeah.
Yeah, you're looking
Oh, I
Facing the
can.
lens.
Yeah.
So now
Is
you
this
got
thing
Thing
on?
Where?
I can't see anything.
You're streaming this.
Okay.
Here's
Here's
the
the
behind
behind
the
the
scenes.
scenes.
What if it was a close-up on a piece of electronics?
Yeah.
Yeah.
Because
It
it should
should
autofocus here.
here.
Yeah.
Yeah.
So
So we'll take.
Yeah, that's
Yeah,
not a bad shot.
shot.
Okay,
Okay,
that's
that's
workable for you.
workable for you?
yeah.
Yeah.
And then,
And then let's
get,
get
push
a little demo here. Get the oscilloscope shot.
Yeah.
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 Oscilloscope's
Oscilloscope's working.
Okay,
Okay,
great.
great.
Do
Do the laptop shot.
Switch
Switch
over.
over.
We got
We
the
got the
protection
protection
shot.
shot.
And we
See
got
the
See the
data here.
Okay.
Switch. All right.
All right. Cool.
Yeah,
Yeah,
let's
let's get on the screen.
Can
You
dig it.
dig it.
Yeah. All right.
That's such a cool setup.
Digging it.
Digging it, man.
Digging it.
This
This is fun. We're getting a lot done now.
Yeah.
Yeah.
Is this all your equipment, Noel?
What's that?
What's
Is
that?
this all your equipment?
Yeah.
Nice. I might want your card actually.
Yeah, I'm just Noel at Sick Luggage.
Okay.
Sick
Like
luggage.
luggage.
Do you have a card?
I
I
gave
gave
out the
out the
last
last one,
one.
but
Let's
let's
just
just
let's just trade digits.
Cool, cool. Yeah, I have a US number now because I'm serious about it.
I like what you're doing,
especially
especially like
I
I have had a bunch of friends who
What's
Are
your
you use
stencil,
pick,
pick,
and
and
bake?
Yeah, hold on. I just did test and it came out better
great.
than my last five.
It's
I think your business is
human cost is like 135,000 people a year, which is ridiculous. They still use it in Southeast Asia extensively. So. But the litigation is $3 billion
So,
a year.
where do you want to do like
Like the settlements.
intro camera?
Lawyers take
Sure.
And then,
Yeah.
So my well, what everything we're doing, or just
no,
what
just you,
Oh, yeah.
you and what you want to walk through.
For the stream. We're streaming now, by the way.
Yeah.
Yeah, all
I hit a button.
Oh, hello.
You hit a button?
Well, it's still on.
Okay.
G'day, mate.
Yeah.
Pop another
I'll try to
narrate
narrate in between,
and,
and I'll give you a camera too.
You give me
Yeah.
a camera?
Well, I'm doing
Oh,
over.
yeah.
over camera.
So I don't know it's watching because we didn't tell anyone.
Oh, okay.
My brother's
No, I saw
watching.
that.
So we got
Yeah,
at
it's
least one.
I'm just waving at him.
Hi,
Andy's brother.
Did he see that? No.
I'm checking right
Okay.
now.
We assume that's your name.
All right. I gotta do something. Maybe can I put this the other way and then I use the thingy later?
I
You can
can do
move,
the camera
too,
over your
yeah.
shoulder.
So
as
I
needed.
think the
Wait, where are you gonna want it to go?
Whoever's in the spotlight gets the microphone that's currently on Morgan, and they get the handheld camera.
Yep.
Yep.
And you just tell me when you want to cut to the handheld camera.
Yeah.
Which
is this
is this
two?
two?
That's two.
So
So if I go,
Where do you want to move to after?
I just like.
Sounds
good. Sounds good. Cool, cool.
Because I can pull this cart out of the way as soon as I'm done.
Are you
are you getting audio from the
cable?
cable messing with you?
It shouldn't really.
I'll just take all the slack.
You know, I look at that and I'm like, yeah, my mum was right. I should get a nose job.
Get a good shirt. Get a good shirt.
But then I've been to the Philippines and like it's like the most attractive thing ever to have a big nose. So
Spend the rest of your life in the Philippines?
You're all good, dude.
it was so funny being that. I was trying to be professional in business. It's like giggling.
Gonna do the exercise first? Camera
Sure.
two?
Two?
Yeah, just tell people when it's
Let's do
Let's
it.
do it.
It's a decent shot.
Do you mind?
Who am I
can
running
move it
this
off
for? The
camera.
camera or
I can move this out, but I'd actually like to do some configuration bits and pieces because it's not working yet. You know, like typical robotics things.
All right.
Okay.
You ready to
You ready to
roll?
roll?
Sure.
All right.
So everybody want to gather around for the demo?
Yeah. Question there was, demo the camera or people?
You should demo to the people and we'll work around. it. Yeah.
People first.
People first. That's what I
People
thought.
first.
All right, so if anyone who wants to check out the pick and place demo, I'm gonna kind of get started. Not just the pick and place machine, but the process that I go through to populate a circuit board. So last year for DEF CON, I made a badge that I call the Cacophony. It's a three-dimensional PCB. So these actually assemble together into an actual shape of a coffin. And there's something like 96 unique parts on here, I think. Go ahead and pass that one around. I think there's something like 96 unique, not unique, there's 96 total parts on there. And hand placing those can take upwards to 6 hours. They're really extremely difficult setup. So I sat down and learned how to use this pick and place machine. And not only that, just learning how to use it, but writing some scripts to translate a KiCad position file to the very odd CSV format that this machine understands. So with that, I'll just kind of run through the process from first using a solder stencil. So when ordering PCBs from pretty much any major house, you can get it shipped with a stencil, and this has all of the footprints for your circuit board and allows you to get paste on your board really quickly. So go ahead and start with that. And I highly recommend the bark card. Works extremely well to get your paste down here.
Anybody wants to see the details of the screen, the people that are on the side.
There you go. I'm back there too. Okay, so just basically globbing the solder paste.
See that mic off?
Did I turn it off when I hit the button?
I think you did, yeah.
I only pressed it once.
Okay.
That's not the one I pressed.
Well, we're learning. Let's see.
You pick them up on the space mic.
Yeah, that's just not going to get recorded on that. No biggie. Just leave it there for a moment.
Just leave it on the side. Okay, so basically this is just doing any sort of stenciling, whether it's solder paste. This is just finely ground up solder in a like a solvent suspension. That's no different from squeegeeing on ink for t-shirt printing.
Just basically push it down and get it into all the holes through the screen. Try to do it in as few passes as possible, but that's hard with this such a large design here. I think that one. Yeah, that's looking pretty good. Okay. Okay, then I can check it out. And it looks pretty good. And because I'm an artist and I didn't have the sense to make a rectangular, completely rectangular frame around this, so I end up having to use this acrylic cutout to hold my work in place. So that gets moved over with it, but that's fine. It can get loaded in here. So this, so the machine is already pretty much set up, and like I said, this is the CSV file that this machine understands. Has a bunch of different, has some of the machine specific settings, and it's got a lot of the job specific settings. It's got descriptions of how all of these are set up, because some of these reels, the parts are 4 millimeters apart. Most parts are 4 millimeters apart. Some are 8. So the comma separated value file that's on there contains all that information. So there's a script that we use to translate a KiCad position file into the format that this understands. This file is not perfect. At the moment, it still places some things in not quite the right spot, but compared to the 6 hours it takes me to do it by hand, it's still much better. So go ahead and run it. It was running pretty good earlier, so I'm going to just fire it off on half speed and see how it goes. Off to a good start. See how it speeds. It's running pretty good, and this is still only 70% of the top speed. So when it's really dialed in, it can run really fast. Sometimes it misses parts. There we go. So this whole set of LEDs, it has trouble placing for yet to be completely understood reason. Everything around it is placed correctly, but for some reason these LEDs are different. I think they're actually meant to be loaded from a different thing. They're actually meant to be loaded from these. Why that affects their place, I haven't quite figured out, but I actually ended up taking them completely off the reel and re-reeling them backwards. And it actually quite a bit. After that, I realized I think they're supposed to be on another one of these corrals. We have. So at a later date, put that back on and see if it can
So this Coffin project, is that what inspired you to start doing this specifically?
I'd already had some interest in like getting working on pick and place. I do a lot of electronics projects and I hate hand placing. But there was just no way I was going to do 150 of these. Otherwise, yeah. Even the fastest I've done is a little under 4 hours to hand place all of these. I mean, that's just on board, yeah. So trying to scale that to 50 was just not practical. You don't bend them, so everything snaps, and then there's actually solder connections. Those solder connections are full structural and active elements. So like this board here actually faces inward into the assembly, and the LED shines down. And the power and data connections get passed through that. Cool. So that's something like, you can applaud the machine if you want. Yeah. That's the machine. So let's see, that was,
What was the success ratio of that? Did it place all of
that was 54 parts. No, there's a bunch of known problems. So, and this is like I said, so if this normally takes me at my absolute fastest, if my absolute fastest, I can do this in about 4 hours. The 10 minutes at the tops, more like 5 minutes of nudging a couple of parts into place, is well worth the time.
So total about 15 minutes, reach actually place the component?
Yeah, exactly. When I was doing these a few weeks ago, from the machine to coming out of the oven, I had it about 16 minutes. So that's a
Very good.
huge improvement. And if I can figure out why these LEDs aren't being placed correctly, I think I can probably get that to about 10. Yeah.
So the paste is still hot, so you can just nudge it.
The paste isn't hot. The paste is just wet.
Oh, you have to reflow it out.
Yeah, exactly. Yeah, that's the next step I'll do after I kind of do this nudger.
More than the pick and place, do ICs or like pick anything off the trays?
Yeah, we do have tray attachments for it. We haven't done any large ICs yet. Well, what size are you talking?
Not big. I'm not sure how to describe the size.
Yeah, and we have the suction. So the big part about that is so much. So one, we do have a tray that it can pull those out of, and then we've also got the suction foot as well. So that's a big part of how it picks those up. It's got like a rubber foot that it uses to make enough contact area with it. Nudging under pressure. I practiced right before this. I'm going for the record. These are actually really good this time.
When that thing was loading the LEDs, I was thinking, I wonder if you put like a high-speed camera on, just to watch what's going on with the LEDs to see if they're like twisted over rotating or
and that's exactly what's happening. There's some of these parts on here that is exactly what happens. Especially when the speed gets turned up.
There's inertia.
The inertia and it causes the parts to rotate. There's a couple on here that happens pretty much. Certainly it'll happen. And so that's a future upgrade that we want on this machine, and it's on a lot of machines. Is that after it rotates it into position, it will go over a camera that will then look at it from the bottom up, and it will see how much distortion it can actually correct for that. So that's a standard feature in a pick and place. One that we hope to get on here after not too long.
That mean it'll probably be more efficient to put it at 30% speed than 70% or something.
Yeah, exactly. If I were actually running these, I would run them at about 50% speed. Yeah, to prevent that, because there's known parts that they rotate. Yeah, I'd rather not do less of this. But this one actually really came out quite good. And then
just to kind of go through the whole process here, you design the whole PCB board. You did some hand prototypes and things like that. But aside from ordering the panelized PCB, you've got a custom cut, laser cut stencil that helps you in laying down the paste. So you first have to paste the board and then you put it in a pick and place. The pick and place is loaded with the reels of all the different parts that you're using.
Yep.
It's dropping all the parts in, and now you're kind of manually doing touch up.
Yeah, and this is what the camera would be
doing,
doing, compensating for if we had the camera on there. All these little slight misalignments.
So the reels are indexed each time it pulls apart.
Yeah,
Yeah,
so
so
I
I
maintain,
maintain,
so
the script that I've written
it not only takes the position
file
file that KiCad outputs or Eagle
outputs,
outputs, but then I have a second file
that
that describes which parts are in which stall. It describes basically it matches the value reference from the position file to the stall number, and then describes things like part size, telling it whether it needs to advance 4 millimeters per part or 8 millimeters per part or 16 for some larger stuff. But everything here is for 4 or 8.
Okay, so that's good.
And then there's a couple parts that just don't place very well, so I end up
just doing
those
those
ones by hand.
Although
I could probably add these at this point.
But like
But
a
like
battery,
a battery
connector,
connector,
there's a speaker here
that
that
is
is the speaker's too heavy for the nozzle that we have on here right now. If we had like the rubber foot nozzle on here, it would be able to pick this speaker up.
Then I have
a switch, which just
always ends up rotating,
so it's just not worth
trouble
putting
putting it on.
And again,
it could probably be
if I had a different tip on there. It's also worth noting that we this is a dual head machine, but we only have one vacuum pump that works. One of the vacuum pumps burnt out. We're hoping to have a replacement of that very soon. And that will solve a lot of these problems where we can put a larger nozzle on the second head, and we'll be able to pick up some of these bigger parts. And then the last one is my main CPU module, which we just don't even have a feeder for, so I'm not sure we'll actually be able to get set up for this in the short term. Okay, that looks good. So with all that, then I pop it out of its carrying frame. And again, if I had actually had if I'd had the forethought that I was going to be running these on a pick and place, I would have put a complete rectangular frame around this. It's just generally a good idea for a whole lot of reasons. But as it happened, I decided to save money instead and minimize the surface area. So then from here, bringing it over to the pick and place, the reflow oven. This is one of 2 or 3 reflow ovens that we have.
So it's rather basic.
These are this really common, cheap,
straight out of
China reflow oven. As they come, they're not very good, and they have even worse software on them. Last year, we took some time to take them apart. The most important part is that we added another thermometer to it, so it can actually tell what temperature it is, which is a really important thing for a reflow oven to know, like what temperature is it really. This has a problem that it has no. As they come, they have a problem where they have no reference against their internal thermometer. So it drifts all the time. So we did that modification to it, and then we loaded a custom firmware on here that just gives better control altogether, including some like features for like custom profiles. I'm not going to run anyone's custom profiles because I think somebody else has been using this oven. You want to get the camera on there? So I'm just running one of the generic profiles, and it's pretty much as easy as just hitting start and easy bake oven. This is about a 6-minute profile, and then you all saw the finished result, and much to my delight, this one passed continuity test without any touch-up, so I'm hoping this one will work just as is.
Getting the multimeter on it, there's a common, well, basically checking all the power rails. So there's 3 different power rails on here, and checking those against ground to make sure that there's no shorts that will destroy it. It's the one being plugged in. So this one looks really good, better than the last time I came in a few weeks ago and was using this machine. So happy days ahead, I hope, because I have a big run of these too.
Do you have a finished prototype?
I don't actually own one. I keep getting drunk and giving them away.
Yeah, it does actually totally work.
they're
Morgan debuted
pretty
these
awesome.
at DEF CON last year. And DEF CON is like one of the biggest hacker conventions on the planet in Las Vegas. Last year was the 27th year that they had run DEF CON.
Davis first DEF CON.
And the badge life community there is insane. Like there are people that now just go to DEF CON to collect and worship badges. And Twitter blows up. Like I was standing next to Morgan in one of the casinos in Vegas, and somebody else tweeted out, "Hey, there's 2 of these coffins in the world, and they're available for the next 10 minutes." Dudes literally ran through the middle of traffic.
Apparently they were like pulling a runner down the in traffic to come and get these badges. And then two more people came screaming in right behind them. Apparently, it was pretty crazy.
It's like Pokemon. You gotta collect them
all. So that's pretty much it. The oven's just gonna run.
So we got this one in the oven. So thank you, Morgan.
Yeah, no problem. If there's any other questions?
The stencil you see.
Yeah.
You can get that from the manufacturer. Export from iPad or whatever.
Yeah, exactly. Just straight from the same export that the actual circuit board is off, is ordered based off of. Well, it depends who you're ordering from. For this case, I actually use Steve Studio in China, and you export Gerbers for them, and then they'll use those same files to generate your footprint. Most of the time, if you have a fairly standard board, you don't do any modifications. You just export them as is. This one has a lot of customization in its footprint layer, and that's mostly because as I tried these, the way that the boards end up connecting together. Like you can see, I've got pads here, but I don't want solder paste on those because those will be hand soldered later. As you can see, actually. There's corresponding pads on the other side, and this is how the coffin is actually assembled. Is that these parts will break off, and like these 2 pads here will get soldered to those 2 pads. And so for things like that, and you can see they're all over here on the tops and the bottoms. Like those are all taken off of the footprint layer. Just because I don't want those cut out in the screen. And actually, the first run of my screen, I messed up and I left a couple on accident. I'm getting there with Kapton tape and taping up the opening. Like, luckily, I learned to screen print a long time ago. I was like, packing tape. That's how you cover up. That's how you get 2 designs on one screen. But Seed Studio and most of the Chinese board houses are great, where you can order your stencil and your PCBs at the same time, which is great because you save on shipping that way. Especially when you're ordering a full frame. Like this one, the shipping is actually more expensive than the stencil itself. So being able to double up on those. I'd already had express shipping on these, so effectively the shipping on the stencil free at that point.
The turnaround time is usually a couple of weeks.
Between a week and 2. It depends. All the board houses like to fight with me on these boards in particular. There's always one argument or another. So these ones generally take a little bit longer, but I'm still getting them another 2 weeks.
Have you tried changing the acceleration and deceleration of the move of this?
No, you can't. No. We've opened it up, and we've got a bunch of pictures of what the control board looks like. It's just an STM32 processor on there, and we do have some grand ideas around doing a full custom firmware forum. Especially, it would be great because these machines are really available. This is called the Neodin 3. It's a pretty old machine at this point. The company that makes this like barely acknowledges the existence of this machine, like Neodin 4. You guys are like, yeah, it's really hard to find information on this machine. If you refuse to answer any questions that I have, they send me to their salespeople and try to get me to buy a new one. They want us to just buy the newer machine. So there's a lot of these available in the secondhand market. So the idea of putting custom firmware on here would be really great, and for that particular reason, to be able to customize those sort of things. But
that might fix the issue of everything getting destroyed that you can slow down.
Yeah, and even I guess even if this machine was still supported, they would probably just try to sell you on an optical system anyhow. So I think more likely that's the route that we want to go that route anyhow. And frankly, I don't want to write a firmware for a pick and place machine. I think maybe one day we might have a good sit down and look for a replacement controller. Somebody is producing a really high quality pick and place controller, then doing a replacement that route might make more sense rather than trying to write a firmware, a potentially limited firmware, so then we can get a newer, hopefully more capable processor at the same time. Support hopefully an open source project that's trying to do a pick and place. Because looking at it from that perspective, this is a very capable machine, and like a lot of these things, just like this reflow oven. The hardware that in itself is really good, and they're just very limited by control software and the limited accessibility of their control software being closed. So I think that would, in the longer term, that would probably be the more sensible route to go, would be to replace the controller outright. Maybe one day we'll do. Vision system next. We really want to get the vision system on here. Yep. The bake here is done. Yes. Yeah. Fresh baked chips.
Is it Ross compliant?
Huh?
Ross compliant?
I'm gonna go with now. All the bits that are supposed to be shiny are shiny. So looks pretty good. Hopefully it's not too hot. So yeah. Looks like everything flowed nicely. So then, the parts that you look at afterwards are basically just making sure that all of the pads, all the solder is shiny. If it didn't reflow properly, it'll have like a gray tint to it. But everything looks good. There's definitely some fixes. There's a bunch of things that are not in the right spots, but I will fix them. That's what happens when you nudge with a crowd around you. But yeah, that's our pick and place machine. We've been putting in a lot of effort to learn all of the crazy little quirks to this machine. I learned something really important while we were setting up with it. So it's gotten a little bit easier to use every time I take a crack at it. So I think we're gonna have our first resident member running his own hardware startup is going to be jumping on this machine and doing his next production run on it to really just kind of put it through its paces. At the end of the day, this is just kind of a hobby project for me to really want to see what this machine is capable of actually trying to run some production hardware through it. So over the next month, we're going to be doing some testing and seeing what that looks like when somebody who has not gone through every little bizarre menu and trying to figure out what does what, see what it looks like when they take a turn on the machine.
Sweet. Well, thanks Morgan and Easy Bake Oven and Pick and Place Machine.
The machines are the real heroes. Hardware heroes, right?
Yeah. To our inaugural hardware heroes.
Thanks everyone.
Can you make sure mic on both, because your mic is still not working.
Oh, really?
Just put that aside for the night.
All right.
It's not behaving and it's not loud.
All right. Put that over there.
All right.
So,
we'll stream to the TV, but if
y'all
y'all want
wanna
to come over here and see it firsthand as
well,
well, you are most welcome to.
So
I'm gonna talk through a few different things. To start with, I'm gonna go with the demo that I know actually works. Be number two. So this camera is kind of fun. It's called a Husky lens. And so we're looking at the camera view here, the business end, there's a camera right there. And then under the silicone sleeve is an open source RISC-V processor. And that's doing basic object detection. So you can see it's putting a box around people that it sees. And then this Darth Vader character is just a battery pack that's running camera. So basically everything is happening embedded and on board on this camera. There's no dependency on the cloud or anything like that. It's just kind of a cool tool for learning basic machine learning. You can train it to recognize an object and track it. I made a really basic musical instrument out of it. I trained it to identify a bottle, and it could track the position of the bottle left to right, and I hooked that up with a pitch shifter. So you can take a musical note and go low, high. Yeah, like a theremin, but just using any object that you want to point it at. So the main point of this evening is I want to talk about one of the tools that's available here in the hardware library of Circuit Launch. And that's this discovery tool here, which if you want to give me camera 2, is this little box here from Vigilant. That's the analog discovery 2. It's a basic logic analyzer. So it has all of these breakout pins. So you can hook up 16 some digital IOs to a microprocessor, to an I2C bus, to a variety of different things. And what I have kind of going in this real world rat's nest on a breadboard is an Arduino Uno board. And then my real target chip here is this 40-pin DIP chip that is a 1980s synthesizer audio chip. And this was used in a really early home computer game called Vectrex, which kind of looks like a Mac Classic. It's just a little box computer, but it used a vector screen and actually painted kind of like the classic Asteroids arcade games. Everything was just a vector image. Am I being Unabomber here? So anyways, this is kind of an in development piece of hardware. This is kind of a rough mock-up of more of my intended version. So this box is just kind of holding the same bits. So we've got one of the sound chips in here and an Arduino to control it. And then a bunch of different buttons and knobs. And I was kind of trying to go for something. Yeah, here, I'll give you a close up. Something kind of like an old computer where the idea is that these 4 bits are actually switching 4 bits in the memory register. So you could say 1 is your first frequency, and you could say 2 is your second frequency, and you could actually use this to bit by bit program the sound chip to make different noises. So do a quick little demo here, see if we can pick it up. When I reset the Arduino, yeah, the volume's not really loud. If you listen closely here, 1, 2, there's this little boopy sound that's happening, and how that is being generated is actually from this little audio chip. And what these things are is, again, this is like 80s technology. So in the early 80s, you didn't have 16 megahertz Arduinos or 240 megahertz ESP32 chips. You just had these tiny little 8-bit processors. And if you wanted to make a sound, you'd have to continually like bit bang that audio output. So these PSGs, which are programmable sound generators, would kind of offload the CPU overhead for making sounds. So what's going on here is the Arduino has an 8-bit bus. So there's 8 digital outputs wired into the sound chip, and then there's 2 kind of state controls. So with the 2 bits, you're setting, do I want to select a register? Do I want to write to the active register? Or do I want to put data on the bus? So you can hear it's making some noise, but it's not working exactly right. And I need to actually debug it in real time. Oscilloscopes are great. I can see the output of the sound waveform and figure out if I'm getting the right target frequencies, but I can't see what data is actually being controlled. So what I have going on the laptop over here is an actual capture with play-by-play overlays.
My partner Chris is like, you're a sound designer.
Thank you, Chris, for the play-by-play overlay. So what we have going on the screen here is the laptop is connected to this logic analyzer, and I've got 4 wires. It's actually an 8-bit bus, but a lot of the registers just use 4 bits. So I'm tapping 4 bits of the data bus and 2 data lines, which tell you are basically your current bus state, read, write, or inactive. And then over here on the laptop screen, you can see here's data bit 0, 1, 2, 3, 4, all the way 5, 6, 7. And then 8 and 9 are telling me, am I reading, writing to the register, or whatever. And so on here, you'll see some different blips. So there's a data blip here, blip, blip, blip. So when the chip boots up, it goes deet, 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 deet. And so all of those blips are where the frequency is changing. So go back to the camera here, and when I zoom in, you'll see that these kind of individual spikes, if I can figure out how to navigate, here we go, are actually discrete bits of data. So down here, we're setting the bus state, and then more importantly up here, we're setting the different values. So if you can decode this in binary, actually have a cheat sheet here. So these are the 16 different registers that you can control, and then the 8 bits of value. So initially, I'm targeting this channel A register 1, and it has 4 bits of coarse tune. So that's what's parallel here. You've got 0, 1, 2, 3, which is 4 bits. And you can see sometimes 1 bit is high, sometimes 2 bit is high. So here we're sending, what is this, 4, 6, 5, something loosely like that. But anyways, this is the actual data that's programming that. So roughly decoded, it's saying select register 1, then it's saying write these bits to that register, and then it's saying latch those bits. And that's the process that's actually generating those tones. So again, this is just kind of a demonstration of how you can more interactively debug the hardware. This is really essentially a software issue, but I'm telling the software, hey, do all of these things, and the software is saying, well, I'm doing all of those things. But without connecting something like a logic analyzer or oscilloscope, you can't really see what is that code doing. And so this kind of initial proof of concept works, but it does break in places where I'm trying to adjust some of the registers and it's not doing exactly what I want to do. So now by kind of going back and forth and comparing the logic data with the software code, I can much more closely fine tune what's actually happening. So anyways, that's kind of the key of what I want to talk about. I know this is kind of like a deep dive in the middle of a vast rabbit hole. So without context, it's a little hard to relate to directly. But just kind of want to give a little bit of idea of the different tools and process that you can take for digging deeper into the embedded hardware. And so that's pretty much what I wanted to talk about. And I think we're gonna get some background now on some microscoping. Although anybody have any particular questions, or anybody else enjoy hanging out and playing with their logic analyzers in the wee hours of the evening? Did you, what was your debugging for the Core 64, or it just worked?
No, yeah. Look at the backside and you'll see it didn't just work. I have one of these.
Yeah.
I didn't use it in that project, but I used
this almost exact same model right here. Oh, you got the logic analyzer option built in here, but
Yeah.
yeah, like I swear the firmware is right. I swear the electronics are right, and it's that connection in the middle. Like that's what you gotta do.
Yeah. Cool. Sweet. Yeah. Thanks. You you ready to jump in? Let me can I pin that on you somewhere? Sure.
Chuck it in. T-shirts aren't great for this. Okay. That'll do.
All right.
Tell us more. Tell us everything.
All right. Tell you maybe not everything. It is a commercial product, so.
So you're visiting us from Australia.
Yeah. So g'day, mate. Pop another shrimp on the barbie, eh? But there's so many Australians here that's not even a novelty anymore. So.
Yeah, they're just saying it all the time.
Yeah, I know. I say g'day. I actually do that. I say g'day, and if you get an email from me, it says g'day. Like that's just normal.
That's how
for me.
everyone knows that you're Australian.
Yeah, exactly. So there is at least a little bit of novelty less, and people will read it and go, "Oh, I love Australians, koalas, kangaroos, whatever, wallabies." Yeah, great, wallabies. I don't like kangaroos. I like kangaroo. It's got a really nice texture, and it's very lean. Yeah, you just pick it up from Woolies, you know. Okay. No, it's not dog food. It's good premium meat. Sorry if there are any vegans here, but they're a pest, and it's dog food, and camels too, and a meat pie. So I'm here to talk. Yeah, if it's a meat pie, it says meat for a reason, not beef or camel. Okay, let me get started.
Did you?
I got a comedy show next week if anyone's interested. So yeah, my name's Jordan Gruber. I'm a mechatronic engineer. I'm founder of a company called Frontier Microscopy, and we're creating a platform to allow industry to automate any standard microscope analysis. That could be in any field, in medical, in agricultural, environmental, whatever it is. As long as there's like a standard microscope type component to it and a scientist that's spending all day looking down it, we want to automate not the scientist, but the boring work that they have to do, because you go crazy otherwise. So we're a hardware and a software company. I would say we're a hardware-enabled software startup, because VCs don't like it when you say you're a hardware company. But we do predominantly do software, and in the course of our development as a business, we discovered that off-the-shelf robotic microscope just costs way too much, and it was something that our customers wouldn't pay. Well, they would pay, but it would be a long kind of enterprise sale type thing. So we ended up developing our own, and it's cooler in every way. I know, because I helped create it. Essentially, what we have here in our robotic microscope is we're using kind of high volume and low volume production techniques to really bring that cost right down. So it's based on an existing base microscope, and we've retrofit it with our own stuff to make it robotic, because none of that existed. None of that existed at an affordable price. So starting from the top, we've got a standard kind of microscope camera that we can swap as we want to. We've got the base, the frame of it. It's designed for a human, so like human bending down and whatever, but a version 2 will not have that kind of. It'll look more like, I'm thinking like a Cybertruck, but it will be a robotic microscope. Then we have optics, so standard microscope optics here. This is our robotic stage. So it's stepper motor driven with pretty standard, actually, quality ball screw mechanisms on there. Do you want me to take the camera? Sure thing. Here's all the secret sauce. So yeah, ball screws operating this through here. We have some low volume kind of production. These are urethane casted plastics here, which are pretty cool. So what they do is they will 3D print a plug, and they'll put that in silicon in a vacuum chamber,
and they'll let the silicon set, and then afterwards they'll cut the plug out in a way that they can then use that silicon as a mold. So you can get, depending on the complexity of the part, you can get between 10 and 20 out of that typically, and it's a resin pour, urethane pour, so cancerous in the state of California. Don't eat it, don't drink it, don't drop this on your foot, don't be an idiot. So this as well, it is post-processed, so that's painted, like I think it's like a spray paint, but you can see like it's really high quality, you wouldn't know it. And by working smart, you can actually bring that cost right down. So all the external plastics that you can see here are actually from using that urethane casting method. There's quite a bit of 3D printing on this as well, but you can't see it. There are like brackets to hold our custom circuitry and so on all over the place, but they're inside. I'm not going to open it up inside just because it's a little too difficult, and there is a little bit of secret sauce in the back there. What else? There is a cool feature which I'll talk about here, which is, it took a little while to get right, and I'll talk about that process because it's pretty cool. We have here a secondary camera, and what that camera does is, I've got a microscope slide here, so if you look at the screen, let me open it up so you can see it, because otherwise I'll have like 10 people crowding around to look at this. No, you have to buy me the beer. Okay, so this is a standard kind of sample. So this is from this is an air filter that's been converted into a membrane and put onto this microscope slide. Why an air filter? Because that's the initial application of our technology in analyzing these filters to see if they contain asbestos and quantify how much asbestos they contain. So an air filter, having air pass through it on a asbestos removal site. Say, I hope you don't know anyone that works in the Transamerica building. I read the lease agreement today, and it was like, there's asbestos in the ceiling, in the wall, it's cladding the pipes, it's in the insulation. So all those kind of famous buildings that you know around New York, here in San Francisco, guarantee if they're pre-1985, they have asbestos in them, which is terrible. So this filter here has just been prepared. There's no special preparation onto the slide. There's a cover slip there on top of it as well. You can see those grid lines. So there's very tiny. They're 100 microns across. So they're tiny. And those grid lines exist as a means for a human analyst to use them to ensure that they're operating, they're analyzing for particles in the correct plane. Because at this very high magnification, and this analysis is done at a 400 times magnification, you often find that you've kind of moved away from that correct plane, and you're either looking at the bottom of the filter sample, or you may even looking at the top of the cover slip. So if you're doing that, you're not looking for fibers in the correct area. So human analysts use those grid lines as a reference. So does Marvin. This is really neat. With that secondary camera there, we actually image the features of the sample, including those grid lines. And from this image captured here of the slide, it's backlit, we can actually map the features of the sample, the macro, and plan how we're going to scan and process the sample in the micro. And so those grid lines being only 100 microns across, from the image captured from here, and considering that the magnification only means that the total image side is only 150 microns across, Marvin's accurately able to zone in right on those grid lines, right on the intersections of the perpendicular grid lines, to use that to create a reference focal plane. That's how accurate this thing is. And most of that is through clever software and some hardware features. So you'd think we might be using really expensive limit switches on here. We're not. We're using pretty cheap kind of standard ones that have some repeatability of like maybe 40 microns or whatever. There's features that are on the physical here that make it so that Marvin can work with the software and perform to the same standard as a very expensive microscope. So if you look here, you'll see these big holes. Well, right next to them, there are holes there, micro drilled, and they're only 200 microns across. And with those holes, they are mapped, that we know roughly where they are. We know exactly where they are because of the precision and accuracy of the CNC process to make this plate. And we know, and if we know where they are from the macro image, we can use that as a way to kind of in our mapping process. We can also use them as like home positions. So a 3D printer uses limit switches, which is fine because it doesn't matter if the part is shifted about a little bit. Like that's not important for 3D printing. But when you're looking at microscope slides, and particularly wanting to zone in on these features, that's very important. So those holes are really cool, serve a very special purpose. I've got another slide here, which is pretty cool. This is called a, if you look at the screen, it's I call it a checkerboard slide. But you'll have 100 of these all over the place in here, I'm sure, right? But we're just doing it the macro scale for this camera, and that calibrates that camera so that we get the performance that we need out of that macro to micro transform. What else? I suppose I can talk about the stuff that is in the back. I won't open it, but in the back of this, I'll flip it around so we can see it. So on the back here, you can see we've got 2 ports. We've got a power port and we've got a developer port or a hacker port. Please don't use it. It's not for customers. We'll probably actually remove it from the PCBA. There's also 2 buttons on here. This is the only physical interface on the robotic microscope. And they're actually quite special because Marvin actually contains his own computer. We're using Edge computer inside the back of this thing. So there's quite a powerful Edge computer in the back. And to operate Marvin, you just need a standard kind of laptop. Any basic laptop will do. I've even run it off my phone. And through, it's a bit hacky, but we use a VNC viewer. And we run a VNC client on the Edge computer. But it works fine. It works absolutely fine. The image quality is good. The controls are good. You know, and the latency is low. We've even run it on pretty like university Wi-Fi, where you got a shit ton of traffic. Sorry about the language, but you've got a shit ton of traffic, and even still we get good performance or reasonable performance out of that. It only it gets the worst around exam time when everyone's kind of streaming Netflix instead of studying. That's kind of the only time it kind of fails. Those 2 buttons on the back there, one just resets our software running on the Edge computer in case there's an issue. And the other one puts it into a Wi-Fi setup mode. So like how you would set up a Google Chrome or, you know, Alexa or whatever. And you can just, you know, you connect to Marvin's setup Wi-Fi hotspot and you enter your local Wi-Fi details, and that's how it connects onto that. We have it set up like an IoT device. So no one really has, you know, control over the software that runs on those Edge computers apart from us. So we use an IoT platform to achieve that, IoT platform software. And that also means that we can push updates en masse to all of our customers, but we can also add applications. So at the moment, we have the application for the air filter analysis. But say we develop another application for, you know, water quality testing is the next one we're looking at. Then if you have one of these Marvins, if you have a Marvin, then through our web portal, you'd be able to click a button and it goes and downloads the application for the water testing. Well, our vision eventually is to be at the point where we have one of these robotic microscopes down to under $1,000. And basically, we can give them away for free even. That's another project. That's a V2 Marvin. It's going to be a mass manufactured product that won't use any kind of existing manual microscope components. Yeah, that's the one that's going to look like the Cybertruck. So yeah, some of the cool software we use OpenCV. We've extended it for our application. We use, say, NVIDIA kind of GPU acceleration here and there. We're looking at technologies like NB-IoT, which is pretty cool to keep these things connected. Yeah, so this is a mechatronic wet dream. I'm a mechatronic engineer, so I can tell you that it is. It's got custom mechanics, it's got custom electronics, it's got custom firmware. We have our own software. We're using a lot of open source stuff as well. And yeah, I'd love to actually, I'm going to throw someone under the bus here, but it's fine. He's my brother. I'd love to demo him for you, but I was trying to get the software to run, and I realized that, well, maybe I'll just show you, and you tell me if you can figure out what's happened. Let me plug in the power. And someone can guess for me. One of these cables. There we go. And the first person who can tell me what's happened here wins a free drink on the house from that bucket over there. All right, let's have a look. So at the moment, I'm just using the hacker port. Is it on? He's not on. So I don't know if you can hear that, but the computer inside is kind of booting up. All right. So can someone tell me, looking at this device manager here, why this isn't working? It's close. That's another problem. That's a different thing. But tell me why it's not working here. Well, yeah. Give me a guess.
Which device is it?
I'll drop the thingies. Oh, that's a lot of thingies. No. I think we're lost. Okay. All right. Can we go back to this screen? I'll tell you. So we have two stepper motor controllers, and then I use the Atmega 32U4. And our head of production, Harrison Gruber, my younger brother, didn't load the firmware on this machine. So the controllers don't have firmware on there, so it doesn't boot. So yeah, totally his fault. I'm sure there's a programmer around here, and I have the firmware. So if you can wait like half an hour. No, I'm not doing it. Sorry, but yeah. So that's what we do. Like I said, I'll give a quick kind of. I'm here. I got here on Saturday. Kieran got here today, and I'll tell you what. He's 17, and he's an idiot. He missed his flight. Not his fault. He missed his flight to San Francisco. So he was meant to arrive yesterday, but he arrived today instead, and he said he'd call me when he got to the airport. He didn't, and he assumed that I'd be where I was yesterday, circuit launch. So he caught the BART from San Francisco International out to here, called me and said, I'm here. I said, I'm not out there, I'm in the city. So he caught the BART all the way back. So he got here off the plane and did a 3-hour detour riding the BART around the place. Yeah, I made sure to tell his mum it was entirely his fault, not mine. But anyway, on the ground here, kind of just getting to know what's happening. Like, great meeting all you kind of people. You're my kind of people. And also looking at moving our business head operations over here as well from Adelaide, Australia. I think we talked about that before. No one knows where that is. Yes. One person knows where that is. Two. Okay, two. And then no one else. It's like starting, the analogy I would say, someone said to me, I guess it's like starting a startup in Nebraska. So, like, there's no spaces like this. This is like, I've never been to an event like this where I am. So it's a cool community. I, look forward to being part of it. If you know people that are connectors or, even investors, we're probably going to do a seed round here that would like to, like, sit down, give us a bit of feedback. maybe even be part of our seed round when I'm back later. That would be incredible. And yeah, that's it.
Thanks. And people find you as Frontier Microscope?
It's confusing. We're not Frontier Bio.
Yes.
We're Frontier.
Just Frontier.
Just call us Frontier because Frontier is easier to say than Frontier Microscopy. And Frontier Bio have been calling themselves Frontier Bio for ages, and I just say we're Frontier.
Any issues with trademarks and other copyright issues? Like there's Frontiers Institute already, that's the conglomerate and sort of.
Microscopy is kind of an odd one. Like most people can't even say it correctly.
Frontier by itself, and that's like.
No. That's just my kind of like. I'm just throwing that around when
Frontier
I meet
is the
people.
shorthand. Well, we'll say the Aussie Frontier.
The Aussie Frontier.
I think we know who we're talking about there. And just kind of like bottom line, what's going on is you've got an XY stage automated with the microscope. So you're able to take a slide and kind of go through it section by section and do some automated processing in the background and just kind of do a higher resolution scan and more in-depth analysis that otherwise somebody would have to like spend an hour manually sitting in front of it.
Yeah, I mean, if you want to know the commercials, you want me to talk about the commercial
if you
bit
have,
of
like,
it?
If we were in an elevator for say 30 seconds
okay.
and you were talking to an investor that
Great.
might be interested.
Does anyone have a couple million sitting around? Maybe? Okay. Okay, all right, sure. So we did the pitch training with Andrea. Let me read the wow statement. Let me find it. Notepad++, my old friend. Is any, Vim or Emacs, spaces or tabs? Yeah, we got that. Right, you don't have to look on screen and me trying to find it. Pitch.txt, great. Okay, so this is the short. So work sites across the US are losing billions of dollars waiting on asbestos testing results. And our technology enables immediate on-site asbestos testing results that not only save lives, but dollars. Dollars, but lives. The human cost is absolutely horrific. It's 135,000 people a year, 3,000 of those in the US. There is $3 billion in legal settlements due to mesothelioma just in the US every year as well. And 60 million of these samples are collected and analyzed at great cost, at $20 on average per sample. So we are selling this as a subscription product. So you pay $4,500 a month, and in that you get 200 analyses. And then you pay on from that $15 per analysis. The reason we've gone about it that way is to kind of hide the hardware costs. It's not particularly expensive hardware, but it's basically if it's a model that works, and so telecommunications are a prime example of that. Like you get your phone free, but no, you're really paying for it. So yeah, that's the short one. And thank you, Andrew, for helping with the wow statement if you're watching at home. But yeah.
Thanks. Matt, your mic here.
May I ask two questions?
Sure.
One is, so you're limited to only having 60 meters?
No, you're fine. Just keep talking.
Okay. You only have 60 millimeters of playroom with a secondary camera that is tracing on how far across each of the grid lines is for each slide that you place for analysis on it, right?
Sorry, I don't quite understand. Say
And then you showed the checkers board for
yeah,
for tracking where the secondary camera is acting or optimizing for. If you have 100 microns across the hairlines that you were showing on the slide itself, and now the secondary camera is off in orientation. Imagine that this thing was turned around in curvature.
Yeah. So if
a square with a diagonal is going to have root 2 as diagonal, root 2 being 1.41. And if now you're focusing on completely 90 degrees perpendicular, then you're dead on flat on something, then yes, it works out perfectly. But if that thing is off by any margin margin of degree,
Yep.
then it's not going to be able to give you a very perfect analysis
Yep.
of what it's scanning.
Yep. Gotcha. Look, these things are not the microscope.
Like,
They're not
it
precision.
takes
I
a
gotcha. I
whole lot
gotcha.
of
Yeah.
development work in order to optimize for it, so I get even the
We
subscription
fixed
model.
it. It's done. It's done. It all works. I'd love to show you. But look, yeah, what you're talking about there, there's a couple of reasons that's a solved problem for us. So, do you want me to? Okay, clip it. Yeah.
What got me interested in asking the question itself was that you decided to go for 3D printing for the fixtures and sort of
Yeah, so
mechanical
let me
parts.
talk you through it, right? So these are put together pretty rough. Like they're not precision machines, but they are microscopes. But they're put together rough, and there's a lot of neat bits and pieces that compensate for that. And you know, say this here, I'll point at it. Or say this here, right? This part. Good idea with a microscope. Thank you. I'm very smart, I think.
Real-time feedback.
I'm not as smart as this guy, but I'm okay. So like this here, this is screwed in. And it's 3D printed, right? So there's all kinds of different, like every unit is quite different. Even mounting the board camera inside this thing, it can be mounted around. Even the lens on the board camera can be mounted out between every component. So to be able to compensate for that, we have two things going on. One is we have those through holes. You can't even see them, but they're next to these big ones, and they are 200 microns across, so twice the width of a human hair. This is the other part of it. So we calibrate for the camera using this. And so that goes...
serves as your reference value?
Yeah, we got those reference holes, and we know because they're machined precisely. They are machined precisely. We know, how far apart they are and whatnot. So this slide going in there, into that slot, and we have a spring mechanism that even pushes it right into that slot. So it's like it's an exact fit every time. Moves out under here, is imaged from the camera, and then through the kind of algorithms that calibrate. There's a calibration file produced for each unit. So far, I've never actually had to I've even removed these covers and stuff like that, and never had to actually recalibrate it with the slide. So that's this unit has come from Australia, and I'm going to take it back with me, and it's going to work back in Australia once Harrison puts the firmware on it. But I've taken a unit from, so this is really odd.
No, it actually started making sense once he said that each calibration file is specifically for that.
For every, yeah, exactly. But to give you an example of how robust that is, weekend before last, I was skiing on a mountain in Switzerland. I was there for business. I was taking the Marvin with me and installing it with a customer there. The unit we sent there, and I'd calculated the calibration file for that unit in Australia, and it still worked fine over in Europe, even though the unit had come from Australia, baggage handlers and whatnot, throwing it around, it was still fine. So that is pretty cool. And how many people are watching? Hello. Don't talk about that one really openly, if that's okay.
Never heard of that.
Yeah.
All right. Well, we'll let you guys talk offline if you want to get more into the weeds. But we do have one more demo, which is some space age retro futuristic technology. So let me mic up. Clip that on yourself there. Bring them over here. Over here?
Over there? Okay, sure.
Stick it on your pocket. Oh, you want to use a chair if you want? Grab a,
Oh,
grab a
cool.
chair
Thank you.
and,
Oh, I feel very comfortable at home
yeah,
here.
right?
This is comfy.
For you.
Yes. Okay, so I'm Andy. This is my Core 64 project. I forget what your name is, but were you talking about learning to do like circuit board design stuff? So, Peter? Okay. So for you and for anyone else who is interested in this sort of thing, so this is the first circuit board I've ever designed, which was like total game changer to me. I did I picked something kind of unique. That's kind of how I roll with my projects, is unique. I did, there's like 8 tutorials by Sean Heimel associated with DigiKey on KiCad or KiCad. KiCad.
Yeah, we settled that at the first KaiCon conference.
Okay, I'm sorry, KiCad. Kakan. So I had very good success with that software and that tutorial, and this was the result. And I had these made by JLC PCB. Crazy, $20. 5 of these things showed up in 5 days before the coronavirus. So that's how this happened. The concept for this is, I think magnetism and core memory is cool. So what? And the unique thing that I did was, hey, could I make it interactive somehow? So I'd found a, yeah, let me back up on that. So core memory is the stuff that put people on the moon. In front of each of these LEDs, I'm going to hold this really steady. Yeah, I was going to do that, my bad. At the intersection of each of those wires is a little black ring of ferrite. So ferrite is basically rust, iron oxide, and it can be magnetized, and being that it's a donut shape, it's a ring, you can magnetize it clockwise or counterclockwise. And clockwise, you would say, is a 1, and counterclockwise is a 0. And there's your 1s and 0s. And that is a form of RAM that was used in the Apollo guidance computer and the computing systems to go to the moon, land on the moon, come back from the moon. It's also has a form where if you weave it in a certain way, it can be ROM. I don't fully understand how that's done, but basically they magnetize them, and whether you weave it through a core or not through a core, a wire, it translates as a 1 or a 0. Okay, so there's this layer of 8 by 8 cores, which is 64 bits of core memory acting as RAM on the top of this. And the real, oh, good video.
Light went up.
There you go. You can see those. You literally hand weave this. So the idea is that this is a kit, and you get to experience weaving core memory. And then there's a teensy LC on the back here, which is, you could call it a variant of Arduino. It's Arduino compatible. It's not an Arduino. Very powerful little universal component. And you can write your own firmware to drive the transistors, which drive each of these wires. And the way that you energize those wires creates a magnetic field at each of the junctions, and you can magnetize the cores. The demo here is sort of using the cores as a touchscreen layer. So I have a magnet on the end of this stylus, and when I come in here, the cores are constantly being scanned by the firmware. They're looking for a state change, and when a state change occurs, it lights up that LED. And so you can do anything with this through firmware. There's a couple other demo modes here, but I want to get back to the first one for you guys.
Question, in their native design, how did they put this? Did they just change the current through there to say, okay, now you're 1, now you're 0? Obviously, you know, they weren't punching their own pens at it.
Yeah, I should have backed up a little bit more, because my mind is like all in core memory, so I just assume everyone gets it, and it's completely obscure technology. Okay, so you've got a core. There's 2 wires going through a core, and they intersect, and the wire, or they intersect in a way that if you energize both of these wires with current flowing in that direction and in that direction. The sum of the magnetic flux produced by that, it's about a quarter amp at 3 volts per wire, so a total of about a half an amp. It creates enough magnetic field that it magnetizes that core in that direction. And if you want to magnetize it in the other direction, you just reverse the current through the wires, and now you've got the other way.
That's sort of the native way of writing the memory.
Exactly. Yep.
So the current flowing through the cores of all the wires, I mean, so the current is also flowing only through one wire, through a bunch of cores, and those cores it doesn't do anything.
Yes, it's called, formally it's called the half select current. So one wire through all those cores is carrying all that energy, but it's only when you have 2 wires that meet at an intersection where you have enough energy to flip the bit to magnetize it. The other unique thing about this is reads are destructive. So you have to write to it. You just say, I'm going to write a 1 to it or magnetize it this way. And there's a diagonal wire that's woven through everything. And that diagonal wire, it's one continuous wire. If the core changes state, there will be a tiny little bump of current in that sense wire. And in the firmware, you say, oh, I tried to change the state to a 1. It did change. Therefore, it must have been a 0. And then you have to write back a 0. So,
Oh, you can do that on a bit-by-bit basis.
yes, exactly.
You don't need another set of RAM to store the values.
Well, yeah, the way they did it traditionally is there was delay lines and these sorts of things where they would store this information. But it's really interesting that you have to destroy what's on the bit to read it, and then you have to write it back really quickly. Yes, yeah. Otherwise, it is static memory. You turn this off, and it's magnets. They just stay magnetized. That's it. And they're not affected by cosmic rays. That was kind of a unique.
And is that why they didn't take transistors? They didn't have them yet?
There were a lot of logic chips involved, but not for the memory side. This was the reliable way to do RAM. And the fact that it was persistent, you know, if the computer messed up and they had to reboot it, RAM's right there. It's just where they left it, unchanged.
You've got 64 bits right there.
64 bits, yeah.
That's like 8 whole bytes.
This demo mode is just showing the extent of the flux of the magnet that's on the tip here. You can see.
When you want to build like a useful storage array, you fill a volume. You don't just do it on the surface. You don't do it flat area.
They do tend, yeah, they stack them. That's right. Yeah. So you can see the flux going on here is it's a bigger magnet, so the flux affects more cores. Anyway, you guys are all free. Welcome to try this. It's just cool, and it's just a side project, and that's all there is to it. There you go.
Thank you.
Yeah.
Is it still used in any practical application today? Or
Not that I know of. I believe if you trust Wikipedia, the last of it was taken out of service as recently as the 80s, which kind of blows my mind because this.
that's defense obsolescence.
Okay, yeah.
Probably they purchased it.
It may have been telecom industry too, like where there was some big switch that I have no idea. But
I remember reading the D52s were one of the last things that had the core memory.
Inside of it.
Yeah, yeah, in the belly.
Yeah, that's so cool. There's a lot to learn about this, but.
To me, as an outsider, it's just fascinating because I feel like it would be something that would make a lot of difference to people that are actually disabled. Like whatever I just happen to have been speaking, if that thing was simultaneously decoding and putting it on the screen for somebody who is deaf, that would be a world of difference right there. And
yeah. Well, these will be available eventually. I want to do a kit on these. Right now, it's on Hackaday.io. So if you want to look it up, Core64 Hackaday.io, and that's where I'm posting updates and things.
Mind starting a
Yeah.
Kickstarter around the auditory unit?
Somebody asked me about a Kickstarter the other day.
Oh, I wonder who that could have been.
Cool.
Thank you.
Well, I want to thank all our hardware heroes this evening with the core memory demos, the microscopy demos, the reflow demos, the logic demos, and Noel, thanks again for the videography, and Leah, Alex, and all the fine folks at Circuit Launch. It has been yet another fantastic evening of hardware hackery, and we'll look to do it again sooner than later. And on that note, I'm going to close with a little Baby Shark, Bit Bang, AT Tiny, 85, Badge Life Ditty. Can I get a sing along? All right. Thanks all. Hi live stream. Bye live stream. Have a good night, everybody. Cool. Well.